molecular formulas. And I think we had left off with just what they are, yes? Simple whole number ratio versus what's actually in a molecule. And the example that I almost always use is glucose, everybody's old friend, the stuff your cells use to make chemical energy. This is a molecular formula. In one molecule of glucose, there are actually 6 carbons and 12 hydrogens and, blah, 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 blah. The empirical formula, so this is molecular formula, incomprehensible writing. Whoopsie. The empirical formula for that same compound is CH2O. It's the simplest whole number ratio. Now, can we have more than one molecular formula that has the same empirical? Sure. So we could have C20, C20H40O20. We could have C2H4O2. Any of those. All have the same empirical formula. Okay, so to go back to our glucose example. For any substance, there is some whole number multiplier that we can use to go from the empirical to the molecular formula. And all of you can look at that and go, oh, yeah, if I multiply all the subscripts by 6 in this one, so in essence, 6 times that, I get that, right? So far, this is not rocket science, Moser. What are you looking so serious about? And this isn't. This is actually pretty easy. What we end up with is a formula that says the molecular formula is equal to some whole number multiplier, some number x, times the empirical formula. That's what we just did. Well, there's something groundbreaking, earth-shattering, oh so cool. Molecular formula mass is equal to x times the empirical formula mass. Huh, that's handy. So let's test this out. We said you can all look at this and you know that, okay, if you multiply all the subscripts by 6, you get the molecular formula. Well, let's figure out the molecular formula mass for that. Okay? So go ahead and do the math. If what I claim is true is, then 180.18 should equal x times the empirical formula mass, and that x should be 6. So what's the empirical formula mass? Well, we got 12.01, 2.02, and 16. I don't have a calculator up here. 30.03. Okay, let me get rid of this. Okay. Solve for x. Really? You don't say. It's 6. Well, golly. I think we got something there. So it's a really easy relationship. It can be explained badly, but it's a very simple relationship. You're just looking for that whole number multiplier. And what you're typically given, the way these problems typically work, is you will be given an empirical formula. So I could give you, CH3. And I could give you, then, a molecular formula mass. So let's try one. So I have a compound that has an empirical formula. CH3. It has a molecular formula mass of 75.2 grams per mole. What I want to know is what's the molecular formula? How do I go about setting this up? My usual would be that I need molecular formula mass divided by empirical formula mass, and that's going to equal my multiplier x. So how do I find my empirical formula mass? Same way you do everything else, Moser. You add stuff. So this means that x is equal to 75.2 grams per mole divided by 15.04 grams per mole. What's x equal? Yeah. So what's my molecular formula? Let me shrink this. If my multiplier is 5, my molecular formula is C5H15. It's a big old hydrocarbon. Okay, that's it. Now, you know what would be really evil? I'll tell you what would be really evil. If you were given a problem that said something like this. This compound is 12.5% bromine, 28.9% oxygen, and squiggle squiggle percent squiggle squiggle something else. It has a molecular mass. I'm not actually really giving you a problem, so you might as well not write this down. A molecular mass of squiggle squiggle. What's its molecular formula? Ooh. What would you have to do first? What can you do from percentage composition information? You have to find the empirical formula. Yeah, which you do by making that magic 100-gram sample and doing the mole ratios and finding the subscripts. Then you've got the empirical formula. Once you've got the empirical formula, you can get the empirical formula mass. Once you've got that, you can do the division with the molecular formula mass. Oh! I guarantee there'll be one on your test. But at least I'm warning you. The quiz that you will pick up tomorrow at some point during the day, I will have it ready by the beginning of second period, so I would recommend that you stop in before too late in the day. We'll have one like that. So, questions, comments, concerns? No? Okay. You've got time to work on the homework. Anybody have any questions about number 35 on the homework? Copper sulfate 5H2O? So this is number 35, I think. This is a kind of compound called a hydrate. So the chemical compound is copper sulfate, but copper sulfate tends to absorb water, and that's the hydrate part. So what we know is that for every 1 unit of CuSO4, it's going to absorb 5 units of water. So when I hand you 100 grams of copper sulfate 5 hydrate, some percentage of that mass is actually just water and can be driven off. So in order to find the percentage by mass that's water, you need to take the mass of this whole thing, so copper sulfate plus 5 waters, and that's your whole. And then the percentage of that would be the 5 H2Os. You're going to, in essence, treat it as though it was that. It's not that because the water is not a chemical part of the compound. It is hanging out with the copper sulfate. So the mass of that is your whole, and the mass of 5 H2Os is what you're dividing that by. Make sense? Try it. One word of warning, I gave the last class this. When I said that these problems start to really build, and I had one of my lab assistants from in the other class who was a chem student last year, I said, you know, what you don't want to do after this chapter is go, oh, I've only got 4 problems left to do. I can do that in the 10 minutes before class. No, you can't. The last 4 problems will take you longer than the first 15. So, just to let you know. But you're going to be well prepared for college chemistry.